he was looking forward, and so this then became the basis for a machine that could compute anything. His discrete state machine could only calculate one function, but a universal computing machine, which is how he termed it, could in fact answer any question that humans could propose. And so you move forward now, and just to summarize that, the discrete state machine had a fixed memory, the universal computing or Turing machine had a programmable memory, and then from that he moved forward to what you could call a universal array, where the output of one machine forms the input of the next. And we can take that even further and to develop an infinite array where the output of one machine forms the program of the next. Now the whole problem here, and the reason I've brought Turing into it, is that in order to give a materialistic explanation of the human mind, we've got to use a very finite machine, that is the brain, to explain what is essentially an infinite output, such as language. So, and you'll see immediately that you can't have a one-to-one relationship between an infinite output and a finite machine. So the machine has to be doing something beyond just have single units which generate each of the behavioral output. And here, this diagram is sort of half a diagram. It's not complete at all. I couldn't complete it. What I wanted to do was connect a whole series of Turing's universal computing machines so that it shows you how the output of one becomes the input of the next. And these machines are linked across to each other. We couldn't do that because the diagram just ended up looking like spaghetti. So you'd have feed forward loops, and you'd have feedback loops, so that the output of one machine could feed back to modify its own input, and it could feed forward onto another array, and then out of this you get a very, very complex model, and you can start to see that this could be the basis whereby a finite machine like the brain can generate an infinite output like language. Now you've got to compare that with the cortical cytoarchitecture. I go back to this picture by Dilip George and Jeff Hawkins. They're looking at the cerebral cortex, and you can see immediately the very close parallels, what would appear to be close functional parallels, but that's not good enough. We want actually something more than just, well, it looks as though it could do the job. We've got to go further than that. That's always been the mistake that people like psychoanalysts and biological psychiatrists have made. It looks good enough, therefore we'll say that it does in fact do it. But that's not good enough standard. And just to show that there's nothing new about any of this, in fact, we go back in history to a British mathematician called Charles Babbage, who built a series of machines. In fact, I think he only built two, which he called analytical engines. And the purpose of this was to mechanize the writing of the very complex tables of longitude, which were essential if Britain wished to be a maritime power. And calculating these took an awful long time, and so he developed a machine called the analytic engine number 1, and in about 1830, I think, and then sometime later developed another one, which was called number 2, and then he drew the design for number 3, but he never built it. He died. He was aided by Countess Ada Lovelace, who was a very accomplished mathematician in her own right, and this of course was at a time when women were deemed not to have the brains to be mathematicians, and she encouraged Babbage and helped support him because he didn't make any money. But he left the plans for this machine that you see here. It was never built, and on the bicentenary of his birth a project was established whereby they used the technology available in the late 1860s to build the machine that he had designed, and this was a project of the National Science Museum in London, and 2 of these machines were built, and you can see a photograph here of one, and over the page is the other one. This is the head technician in charge of the program. One of them's in California and one of them's in London, but I've never seen any of them yet. I'd really like to. And the first time it was used, it worked perfectly. So Babbage certainly knew what he was doing, and he was mechanising what had been considered to be a quintessentially human property, that is, the capacity to calculate mathematically. So, coming back onto Chalmers' model, leaving experience aside, we can in fact bridge the gap between the brain's data processing capacity and Turing's theoretical principle of mindless decision making, but not with a 3-pin plug. So we've been looking for a plug that would go from mind down into the brain and then transmit the information that we want to get from mind to brain. We use what are called logic gates. Now, unfortunately, my slides are going to start getting a bit complicated from here on. This logic gate is simply a machine which performs logical operations. That's all it is. The simplest logical operation that can be performed by a machine is negation, or the NOT gate. And this simply takes whatever the input is and turns it into its opposite. It switches it off. So if it comes in positive, it goes out negative. If it comes in 1, it goes out 0. If it comes in hot, it goes out cold. It makes no difference. The second step is the one I've got drawn in diagrammatic form, which is a series of switches. And these switches function as an AND gate. So it gives a theoretical account of braking on a red light. So you've got two processes, two switches which can be activated. The first one is activated when the circle is recognised, so that closes gate 1. And the second one is activated when the circle is recognised as red, that closes gate 2. So then a current can get through which sends a signal straight down to the effector organ, which in this case is your braking foot. So instead of thinking there's something magical about humans braking when they see a red light, it's just a very simple process of having a logic gate, a mindless gate that will do that. We can recognise circles. You don't have to have any human mental properties to do that, because birds do it all the time. And we can recognise red, well, birds do that too. So there's nothing complicated about that. And out of that, a simple model of why people brake, or how people brake on a red light. Of course, in Darwin, nobody brakes on a red light. They hit the accelerator and go faster. And now the whole point about logic gates is that they are machines which co-opt the material function of the machine to perform a logical operation. Physical machines, such as the switches, simple switches, function in a physical space according to the laws of thermodynamics and of the time-space continuum. Minds, on the other hand, function in a semantic space according to the laws of logic. And the whole problem is to try and bring these two together so that the semantic space and the physical space actually touch without breaching the laws of thermodynamics. And a logic gate is the process by which we do that. A logic gate bridges the two realms. And just compare that with the soap molecule, which has got a hydrophilic end and a lipophilic end, and that way it can bridge the gap between, or the junction between fats and water. Now, machines are about material relationships in the physical realm. That's what machines do. They just perform physical jobs called relationships. And meaning is about logical relationships in a semantic realm. And a logic gate co-opts the mechanical function of a machine in the physical realm to acquit the semantic function of defining relationships in the semantic realm. A single logic gate functions in a law-like manner in two ontologically distinct realms. And this, of course, is the final triumph of dualism. And on this point, the whole project of defining a monist model of mind collapses, because people like Dennett and Searle have always said you cannot join the two realms, that if you define them as ontologically different, then of course they can't touch. But that the whole project collapses, because here is a means by which they do touch and interact without breaching the laws of thermodynamics. The logic gate passes information between the physical and the semantic realms with no breach of the law of the thermodynamics, just because of its dualist function. It functions in two realms, and that's critically important to remember. Second point to remember here is that information goes both ways. It goes from the physical to the logical realm and from the logical back to the physical. And that, of course, is the end of biological reductionism. The whole point of biological reductionism is to show that the mind